So we will begin. Before we start, I'd like to say a few words about Professor Oliver Braddick, who passed away on January 17th this year. Ol was a great scientist and thinker, and at the same time, a kind, humble, and caring man. And together with Jan, they pioneered investigations on the development of visual perception in infancy and childhood. We were very fortunate to have Ol and Jan not only give a joint talk in our seminar last year, but also attend many of our seminars and the discussions that followed. It is a great loss to all of us in the vision science community, and our hearts are with Jan and the family. You will be greatly missed, Ol. May your soul rest in peace. And now to today's seminar. So it is a great pleasure to have with us today in our seminar, Professor Shimon Ullman from the Weizmann Institute. Professor Shimon Ullman did a BSc in mathematics, physics, and biology at the Hebrew University, and then continued to a PhD in electrical engineering and computer science at MIT under the supervision of the legendary David Marr. He then became a professor both in MIT and the Weizmann Institute. He is the former head of the Department of Computer Science and Applied Mathematics at Weizmann, and today he is the Sammy and Ruth Cohen Professor of Computer Science at Weizmann and also the director of the Weizmann AI Center. He is the co-founder of Orbotech and a former member of Israel's Council for Higher Education. He has more than 32,000 citations and an H-index of 65 according to Google Scholar. Some of his publications have thousands of citations each, as the influential publication with Christoph Koch, Shifts in Selective Visual Attention Towards the Underlying Neural Circuitry. He is the author of several books, including The Interpretation of Visual Motion, Image Understanding, and High-Level Vision, Object Recognition, and Visual Cognition. He won multiple prestigious awards, including the Israel Prize for Computer Science, the Emet Prize in Exact Science Robotics, the Rommel Hart Prize in Human Cognition, and the Azriel Rosenfeld Lifetime Achievement Award in Computer Vision. His research focuses on vision from the perspectives of both human vision and machine vision, and he tries to understand how the human vision system works and how one can construct artificial systems with similar or even better abilities. So without further ado, I'd like to welcome you, Shimon, to our seminar to hear about your work, and thanks for joining us.
Thank you very much, Sharon. Let me just make sure, is it visible? And
yes.
Oh, I see some of the people. I don't have the full gallery. So hi, Jeremy. Nice to see you from from afar. That's one advantage of having these seminars via the Zoom. So you can see the title here. I'd like to talk about human-like scene interpretation by a brain-inspired model. And I think that what I mean by human-like and brain-inspired will become clearer as we go along. And the topic is to understand how we understand complex scenes. When we as humans look at scenes like this, and this is complex, most of us have not seen something like this before, but we understand immediately what's going on, what the people are doing there, and what happened before that caused this scenario, and so on. So this is very natural for us, and we do it very well. And this is something that we cannot do, and you cannot even approach in current computer vision systems, and I will note about this a bit more as we go along. And here I'm showing some of the difficulties in scene understanding become apparent when we see a nice scene like this. And I use it partly because it was a couple of years ago, it was circulated widely in the computer vision circles as something that sort of is a challenge. Let's see if we can ever get to understand automatically scenes like this. And you can see that it's a scene with complex meaning. It's not just labeling a class of objects or something like this. We focus on sort of the important things in the scene. We don't need to go over the entire scene and recognize everything. And at the same time, we pay attention to sometimes selected details, like what what is happening here. Um, just to make sure that you're with me, can anyone unmute themselves and just say briefly what's happening in this image? I'll be glad if someone would volunteer to just say in
Somebody just put
King
on
the guy
extra height.
heavier.
Yes, Obama is.
right. So I think we all understand the story behind this, and you'll agree that it's crucial to understand also this particular detail. And also, there is clearly combination of vision and some non-visual knowledge. We know about the act of a person weighing themselves and what they have in mind when they see the scales and so on. So all of this is part of the interpretation, and all of this comes together very quickly during the scene interpretation. And the fact about small details is crucial. Well, I'll go into this in a minute, but I'd like to note also that scene interpretation is something that comes very early and very natural for us. So even relatively young children, that's what they do when they look at images. They do not name or label objects, but they immediately understand the story behind the image. So for example, you can see the description here of a 3.5-year-old, and you can read it. He's angry because he hit his cat with the ball, and you understand what's going on. And this happens at this age. So clearly it's not something advanced that we need to grow up and have many years of experience before we get to the stage of understanding scenes. And in computer vision, we have a lot of experience with solving vision problems, and scene recognition has been a major part of computer vision from the start, and we've not reached a stage that we can understand it at the level that that young children can do it. Now, in computer vision, we have made really amazing progress, and many things are working very nicely in using current models based on deep networks. It started with single object recognition, the famous ImageNet competition, where computer vision was able to recognize very well very diverse images of different classes. Like you can see elephants here, very different images, but these are being recognized very well by computer systems. And it's pretty amazing, not only that the performance is good, but with these new advances, the systems learn automatically from examples. They don't have to be programmed to do exactly what to do. On the other hand, they paid the price of very detailed annotations, which is problematic in general, and as we'll see, certainly in scene understanding. This is a representation of the state of the art, trying to move beyond single objects. And this is from a system called Mask RCNN. It's the end product of many people working over several years at it's now metaverse, I should say, not anyway. And what you see here is that the system, the model is able to recognize not only a single object at the center of the image as in ImageNet, but sort of multiple objects, in this case focusing on people, but it can recognize a variety of objects, and are moving recently in some recent versions of this system, people at Facebook, to recognize also parts. They don't have it for many objects, but you can see here sort of at least a nice demonstration of recognizing people's parts, the sort of a skeleton of all the limbs and the head and so on. So this is roughly the level that going towards scene is to recognize and segment objects and to some extent object parts. And as I mentioned, the ability to recognize crucial components in a scene can be sometimes quite minor and small. For example, again, if someone can say, is this guy smoking or not?
No, it's a crayon.
No, and the crucial point is here, you have to pay attention to this component of the scene, otherwise you'll miss the point or the meaning of this scene. So you have to recognize these objects and components and so on at the level that will be able to capture, whenever it's necessary, to capture also small details. And therefore, the recovery of all components in the scene is really a very challenging one. And when you look at a scene like this, if you would really want to go in the way that mask RCNN, this model that I showed you, that the goal is to do as a first step towards scene understanding, to recognize all the possibly relevant components in the scene, then clearly in a complex scenes, this will become virtually impossible or entirely infeasible. And at the same time, not only is it infeasible, which is a problem by itself, but even if we could do it, this is insufficient. And the reason is that components are not enough, but the entire configuration is important. So this is just a simple demonstration of this, that the main components in the two scenes are very similar: two boys, a fence, a ball, but they have very different implications and interpretation. That on the left, taken from a pretty well-known movie, the two boys we guess that they would be happy to play with each other, but they cannot. On the right, they could play together if they wanted to, but apparently they prefer to sit and talk. And this is not because of difference in components, but because of difference in the structure, in the relations between the people, the ball, the objects, the ball, the fence, and so on. So in fact, what we want to get out of the image is not a list or even with segmentation of all the components in the scene, but we want something structured in the sense that it contains relationships between objects and properties that belong to specific object. And this is a simple rendering of something that we would like to get out. This is a depiction of a structural description that has the components and associated with them the properties and pairwise relations between objects. So the goal, the initial goal, or part of the story of scene understanding, is to go from images to structured configuration that will allow us to get the meaning of the scene. And people in computer vision are moving in this direction, trying to construct what's called in the jargon in the field a scene graph. It's a graph describing the scene. And you can see here that it's an output of a particular system, and they show the main objects that have been detected, the components, and creating a graph structure from which you can read more detailed and sort of structured information. For example, that the hand of this woman is holding the hand of a man who is wearing a jacket. So we can read all of this from the scene graph, and that's the form of the output which is used to describe scene. And I think the details can be debated, but something like a structured representation like this is important. And here is sort of the state of the art in trying to get something like this. You can see a scene here, and the sequence of operations in which they start with the mask RCNN, in fact, with this particular algorithm, and they extract as many scene components as possible. And then they look at all the pairwise, all the pairs of components in the scene, and there can be, as we said, many components and of course, many pairwise relations. They try to compute all of them, so eventually they get a final description of the components that have been identified, the relations that have been identified, and so on. So this is sort of the direction. Now, as I was sort of building up the argument, I think that this will not apply to really dealing with the complex scene. It will be infeasible to do as a first stage a full scene graph of an image, image like this. And instead, and this is the idea that we sort of motivated us in the model that I'm going to present, is that we can have an image, and together with it, if you give a particular task of interest, then sort of you can come up with a very wide range of possible tasks of many different types, and you just answer them by looking at the scene. So for example, suppose I ask you, are there in the image people now crossing the street, people on the crosswalk? What's the answer in your view? Again, anyone
Yes.
volunteer? Yeah,
Yes,
right.
there are people.
Here is a more complex one, and I hope that the image is large enough on your screen because it requires some details. Do you think, is there or is not any taxi in the image in which we can see somebody currently getting into the taxi, say? Or is it open door?
No.
No, and the answer no here is even more complicated. You have to do quite a lot of things, but we can do it.
On the left.
Oh, sorry?
Yeah,
This is debatable. You can see, we can debate and we can know exactly where are the more suspicious places. So we can analyze it. Right, we analyze it very well, even though it's, and I could have, listed here any number of the different tasks we get it. So getting a full scene graph is impossible, but getting out relevant information that you're interested in, once you have it, then you can go ahead and get the task. And I think that that's what people do, and I think that that's what machines should do too. That it's a mistake to try to get a full scene graph and then think what to do with it. But the natural way and the practical way is that you have a scene and you have something that you're interested in. And the problem then is, how do you get the thing that interests you out of the image? And the model that I described goes along this direction exactly, that we have sort of a guided visual system that gets, that is not like the standard deep network model in which you get an image as an input, and then you get the full solution, whatever you want here as an output, namely in this case, a full scene graph, a full scene description that will tell you everything. But what you get is a sort of a system that has two parts, one guiding the other. You have on the one hand the usual bottom-up network that can do various recognition tasks and segmentation tasks and identify relations and so on. And also you have a way in which you can insert to the system a goal that you have, or something that you would like out of the image. And this is done by the top-down red schematic network here, which then guides the bottom-up network to output whatever the goal dictates, or whatever the instruction is. So this is the very general structure of the scheme. And just as an example, what I mean by giving it a task or a particular task, what will come out. So you can look at this image that we see here on the screen of the man doing something to the bag and to the woman. And in this model, in the way that I'm going to describe next, how all of this is happening, we can ask at the moment, for example, what is shown here as touching, man. This means is what the man is touching. And suppose I somehow point to the man, or we know which man we are talking about, and the question is what the man is touching. And if we have the image and we input to the model the instruction that we want to know what the man is touching, you will get that the network answers the bag or the purse. If we keep the image exactly the same, we do not change the input in this sense, but we do change the other part of the input, namely what is currently the requested goal from the system. Sitting chair, and this means who is sitting on the chair, a particular chair here. You can all look at it. The answer is the particular woman, and that's what the model that I'm going to elaborate will will do as well, it will output the particular, an answer to the particular task that has been provided to the system. I will, within very few slides, I will describe some detail, the structure of the model, but there is no time to go on to all the fine details. You can answer at you can ask me at the end, and I also give you at the end a reference where all of this is described in great details. So the model structure, we already saw sort of the very skeleton that it has a bottom-up stream, a top-down stream, two inputs, and so on. Here, each circle in this diagram at the moment is a complete level in the multi-level network. Here is a small representation of a small part of the network, but just this is at the level of units of neurons. So each circle here is a unit in the network. The green one is the bottom-up network going up, and the red one is the top-down. In the way we implement it, and there are good reasons for it, which I will not elaborate too much, but they are a copy of each other. So the red is just basically a copy of the green, but going on in the opposite direction. The connections that whenever there is a connection going up on the green network, the bottom-up network, there is a sort of a counter part in which there is a connection between the corresponding unit on the red network. We sometimes refer to it following nomenclature in the literature as a counter stream structure, that we have very similar streams going in the opposite directions and interacting bidirectionally between them. A technical issue is that we use standard deep network training to train this bottom-up, top-down network. The network is a recurrent one. You can see that the connections are going in both directions between the bottom-up and the top-down streams, creating loops and creating a recurrent network. And the standard way you can still train such networks, although for deep networks, the network needs to be one directional, needs to be sort of bottom up. And the way this is treated in practice is that you use what's called unfolding in time, in which you follow the network for a few iterations. In this case, it's only for sort of 1.5 iteration. The initial flow is through the bottom-up network. Then there is a flow through going top-down. And then, because it's recurrent, there is another flow through the bottom-up. And this is drawn here in the model as another piece of the network, with the constraint that the weights in this bottom-up 1 and bottom-up 2 stages need to be identical. So in this way, you can train. You do not really think or treat this network as having many different components. It's this network in which things cycles around. But the way you have to deal it, and in order to apply standard backpropagation, is in this way. And you will see in some of the drawings of the network later on, there will be this kind of 3 columns in it. It's the standard bottom-up, top-down, but just to show the way it has been really trained. And the input is always 2 inputs: an image on the bottom-up part and a top-down instruction coming from above. And let me mention here that generally the structure of a bottom-up and top-down in an iterative, bidirectional connection in sort of this recurrent arrangement is really a hallmark of cortical structure, and I will not go into the details. But roughly now, it has been a long time, and only in recent years we found more, the community, about the structure, that the input goes to layer 4 of the layers of the cortex. From this, it goes to layer 2, in fact, a combination of 2 and what's considered 3A. Sorry, that's I'm sure I'm pointing to the top down. 4 and then to 3B, which is the bottom part of 3B, and then to 4 and 3B and out to the next area. On the way back, it's going to 2 and parts of what's considered 3A. There are connection to 6, and then actually from both these levels, there is the continuation of the feedback downstairs. So this is in part what I meant when I said that the model tries to be motivated by cortical structure in a way that is not motivated. It's not being done in current systems. This arrangement with bidirectional connections is not used in current computer vision systems. This is a more technical for those who are really into deep networks. This is ResNet 50, if I remember correctly. And it's shown 3 copies of ResNet 50 of a network actually used frequently in vision tasks. So it's the standard, using standard components from deep network building blocks, but arranged in somewhat special way. And the main special part is this part here, which is where the top-down instruction is being inserted to the model. You tell the model what you have in mind and what you want to get out. And let me go quickly through how this is being done. This is an enlargement of this part. And we put in what we want, like the man grabbing something. So the task will be to find what he's grabbing, and the argument will be the man. So what to take, what to compute, and what task you want to carry out, and what to apply this task to. This is the argument. So 2 vectors, we'll see these vectors in a minute. They get into as 2 long vectors, they get in, and then there is some learning going on, and eventually this sort of propagates through the entire top-down network, and through the lateral connection, it influences and modifies and guides the bottom-up network on the next cycle to compute what we ask it to compute, like the touching man. Touching is the task, man is the argument. We tell the system we want touching with a particular person, and the network complies. Let me give you a more specific example. Here, the task is we have 2 people here, and we want to take out their properties, for example, glasses, hairstyle, shirt, and so on. And we give the instruction in a very symbolic way that seems to have no meaning to begin with. For example, if we have a number of different properties in mind that we want to take out, say 7 different ones and 10 different persons, then the way we specify the property and person to now give to the network is simply by, we want the 3rd property of the 7th person type. So if we want the hairstyle of John, and John is also known as person 7, we give this very symbolic inputs into the system. The system during learning learns to interpret or to hear that everything is learnable. So it's very interesting to follow the network. So eventually it converts these symbolic commands into some elaborate representations which tell the system for the system they have a meaning, that this is hairstyle and this is John, to focus on these things. It's interesting that the networks learn this very well, creates this representation that guide the system to do what it needs to do. Now, having this model available, here is the crux of the matter. What eventually, for scene interpretation, what we want is, the main goal now is to apply sequences of top-down instructions in order to extract from the scene structures of interest. And let's see how this is done. And the way we have dealt with it, or studied it and developed and tested it, is we created a data set which is computer generated, and for scene interpretation, you want to be able to create rich scenes with people and objects, and people interacting with each other and with objects. On the other hand, it's very difficult to just find such scenes that you need in the internet, say. So we created our own scenes, and they contained human figures, and they could be men, women, boys, girls. There are also a variety of objects. The people can have different properties, and they can do various things, various relations, like facing each other, holding each other, holding objects, or touching each other, and things like that. So we can create relatively complex scenes with agents, objects, and interactions between them. And during training, we first train the scheme to classify all the objects, properties, and relations individually. So if we want to know, to be able to ask what a person is holding, we have to first individually train the system on the relation holding, in which we give it an instruction, a top-down instruction of a person and a symbol for holding, and then the loss of the function that it is trained on is to give the correct answer what this particular person is holding. And as I mentioned before, this is the training goes. It's a nice property of deep networks. They can do it, and they give you, given the image and the task, they give you the correct answers. And in human vision, there is a huge number of objects that we know about, of relations that we care about, and properties. And if you wanted to completely simulate human vision, you will have to train the system on each one of these individual aspects. And this is, I think, inescapable. If you want to be able to recognize a particular, a panda or an F-16, you will have to teach the system to recognize these individual objects, and similarly for properties and so on. So this is for recognizing the possible building blocks of a scene. But the main aspect is to go beyond this, which is what we in fact have a lot of progress with, dealing with the individual atomic components of a scene, but and go towards analyzing complete structured scene. So the real difficulty for us is not the training the individual constituents of a scene, but to use sequences of top-down instructions for scene recognition and scene understanding. So let me give you an example of what how this proceeds in our system, and the point is that we want to give the scene interpretation scheme an image and some goal in mind that we can change, and we can give it sort of a really one of many possible. You can just come up with new goals that you might have in mind. And what I want to show you is how, given these two aspects, the system generates on its own the appropriate sequence of individual top-down instructions that, taken together, will guide you towards the correct answer to the goal you retrieve for you, the goal you gave to the system. And I mentioned that we train on individual objects, relations, and properties. And perhaps somewhat surprising thing is this is all the training you need to do. You don't train the scheme, the model directly on scene interpretation. It just does it on its own once it has in its capacity the ability to recognize the individual objects, properties, or relations that are necessary to complete the task. So let me show you an example, which is a real output of the system being shown a particular goal. We'll just follow the sequence of internal steps that the model went through. Let me show you how it evolves over time. What we see is in the image. And here is a representation, which is the way we use to give the system a particular goal. What we give it is a particular structure that is of interest in this image. So what we see is a little graph, and if you follow it, there is a boy facing a woman. The woman is holding something, and what we want to do is to find what the woman is holding. Of course, we want to find the boy, we want to find the woman, and we want in this way to get from the system from the interpretation process, this particular aspect of the scene. So I'll just tell you, observing what the system sort of did one step after the other. Everything is done automatically with the sequence of top-down instruction is generated automatically by the model. And what we see here is what it chose to, what kind of top-down instruction it chose to apply at each stage. You can follow the logic of this. I will explain a little in the next slide a little bit more on how this is done. The point now is just to watch the sequence. The scheme, when it just opens its eyes and looks at the scene without any prior analysis of it, it extracts objects and people in the scene from, we selected it to be from near to far. We also tried things like from the center to the periphery, but this is a minor consideration at this stage. But it just explains that the first thing that was extracted from the image is this woman, because she happens to be the closest person to the camera. The system then asked whether this woman is facing anyone. The answer was of the network was none. She's not facing anyone. The next command was to extract another person, which happened to be this girl. Again, it asked about facing. There were a number of stages that system went through. The next interesting thing is that it got to this boy. It found that it's facing a woman. And then the next command was what this woman is holding. The answer was a paper bag, and this completes the goal that was here. You can see that the interpretation was partial. It sort of went through a number of people that it found that it had to go through, but ignored other parts of the scene. You can see that at the end, it's not just that we get the label that it's a paper bag, but we classify, and we also segment, as you can see here. We know that the woman is here, and we have our segmentation here, where the boy is, where the bag is. So we get, in this sense, a detailed interpretation of the scheme. In fact, I don't show it here, but we get the sort of the graph, the part of the scene graph, which has to do with this particular participants. And I also would mention that it looks like sort of a program applied to the image. You cannot really pre-compute the full sequence. What will happen at the next stage depends on whether you found something or not. So it looks more like a program sort of unfolding in time applied to the image. Now, beyond the scheme, beyond the scene, there is, of course, an algorithm that needs to find the sequence of instructions. I will not go into the details of this algorithm. Again, the algorithm that get the input, the image, and the goal, and it on its own, it sort of emits one by one the next top-down instruction to apply to the model. I will just spend a slide or two saying something about the idea behind the algorithm, because the main point maybe to say is that what makes this algorithm possible is that you can ignore the details of the objects and the properties and so on. If you had to, then you will have to be trained with many images of different objects and different properties and so on. And it's very important to not rely on this, but to just, without having detailed examples of anything, just go ahead and be able to interpret the scene. So the point I want to mention on using this slide is that what the algorithm does depends on the abstract structure of the goal, and not on whether you're dealing with a woman holding a bag or anything else. So for example, suppose that you are interested in finding a particular structure in a scene, which is a red car, which is to the right of a yellow bus. That intuitively, you could go one way of identifying such a structure is you find a bus, you check that it's yellow. If not, you look for another bus. If it's a yellow bus, you look to the right of it and you look for an object which is a car and has the color red. But this is entirely true if all I tell you is that I'm looking for two objects. One is an object of class 1, which has a particular property P1, and then there is a relation to another object which has these characteristics. And then I will find one, I will check the class, I will check the property, I will use the relation to go to search for the other one, and so on. So basically the algorithm works on this level. It's described, characterized at this level, and then you can add objects, you can change relation, and so on. You don't have to train on any particular configuration. It will get the structure and follow the abstract structure in order to find what you need. So there you get an image and a structured graph. And let me also say that it's becoming a little bit clever and a little bit sort of with some cognitive understanding. You can challenge it with more complex graphs. For example, suppose I ask you, the question is everybody looking at the speaker in this image? Again, a volunteer, can you say yes or no?
Difficult.
But what do you think? Is everybody looking at the speaker?
I would say more yes than no.
Okay,
I would say
yes.
the person on the
right.
right, I'm not sure.
You know, this person?
Yeah, I don't know. Maybe
Well,
looking
you look
even
closely,
further
look
away.
at his eyes, look at his
Yeah, I
eyes.
think he is.
Yeah, probably, I would say probably yes. I mean, in many of the things, you may be not 100% sure, but less than that. I would say probably yes. Liad, how do you any feeling, internal feeling, or how do you solve this problem?
You asked
Just
me
look and say yes,
like,
or do
I had a gist. So first, like my first response was based on a gist
okay.
assessment. Everyone just seemed to be looking. And then when Sharon said, well, maybe not, then I moved one by one.
You have to verify and write. So in some sense, as I'll show you, in fact, I think that you do more sequential processing on particular subtasks, as you may think, and I'll get to it in a minute. That I'll try to convince you also that you know that this sequential processing is in fact happens even in situations where you are not aware of them. I'll show you at least one example. But let me show you that the algorithm that we do, you can give it goals at this level of complexity. For example, find all the girls that are facing other girls. So you have all and things like that. You have this is a logical quantifier. It's not just in a simple graph. You don't have logical quantifiers. We understand exactly what all means, and this is sort of a more cognitive understanding, and we apply it. We apply it here just to, without getting to the details. This is the image. We have this question, and it does whatever it needs. That it finds these are the two girls that are facing each other. This is a counterexample. She's not facing, and so on. So there is no problem for the algorithm to get goals at this level and find the answer by generating the internal processes, putting them together in doing this. So the relevant structure, scene structure, is recovered in the model incrementally, and human vision does the same. And Liad, this is what I meant is the example. This is an example from a psychophysical study, so I'm not going to talk about it, but in addition to all the computational work, we are running quite an elaborate psychophysical study on people analyzing complex scenes. So we have something called the complex images psychophysics. It's done with me by Dani Harari and Hannah Binoni, who is a psychophysicist. Liad, you probably know her. And in this study, we show people complex images, and we show the images for variable time beings. So a person may see the image only for 50 milliseconds, or 75, 100, and so on. In fact, all the way up to 2000 milliseconds to 2 complete seconds. And you can imagine it's a lot of work and a lot of subjects, because we have 20 subjects, and each subject see only one time being. So for the 50 milliseconds, we have 20 people. For 75, we have 20 different people, and so on. So we complete this complete study. And what we measure here is what people get out in 50 milliseconds, 70, 100, and so on. And here I will not go into detail how exactly we do this, but this is a depiction of what people get over time. At 50 milliseconds, they only get the girl. It's girl child because some people do not even say that it's a girl, but say a child, but this is, everybody says that it's a girl or a child. Note, by the way, that the girl is a little bit obscure, obstructed here, and so on. Nobody mentions the red object here. People focus when the time is very limited on the girl. At 75 milliseconds that she's holding an object, 120, then it's pouring. Only here at 200 milliseconds, people get to the funnel. The bottle here gets noticed and interpreted and incorporated at 500 milliseconds. Now, I have not shown you this image in isolation, but if you look at it, you would say, as Liad maybe said, I looked at it and that's the gist of it. I see the person pouring, but I think there is quite a lot of structure going on here throughout time. And we use this, or it is planned to use, we're just beginning to use this psychophysics. It's potentially useful for evaluating the model and watch the evolution over time in the model in people. The last part of the talk that I want to go into is that the same model solves another problem, which is less obvious to people who are not in vision and not maybe in network modeling, but it's the problem that really plagues not only image interpretation, but problems in AI outside of vision, which is called combinatorial generalization. And let me tell you what this combinatorial generalization is all about, give you the evidence or show you that deep networks, for some reason that we or people in the field do not completely understand, but the deep networks fail in quite a fundamental and problematic way in this combinatorial generalization, and what happens in our model. So the thing is that in cognition, you get not only in vision, but in language and in cognition in general, into the issue of sort of structured representations, when you have graph-like structures of objects, relations and properties and so on. And here is an example of, for example, just showing a graph for this sentence, a brown dog chasing a terrified cat, for example. This is the dog chasing and so on. The same graph may have the same structure, but different components, that a large cat is chasing a furry squirrel or whatever. And of course, you don't want in vision, language, cognition in general, that in order to understand things, you will have to see for every structure, all the combinations, all the possible components that may be participating. Will not be enough to see one of them, but both a cat and a dog and whatever they're chasing, you will have to see examples of everything in order to deal with the structures. And that's the combinatorial part. Large structures are combinatorial, and if you have to see every assignment, every configuration of possible components, and of course you are out of business. You want to generalize easily from structures built from some components to similar structures in which the components are replaced by other components. And I can give you a number of citations. I chose one, but people independently ran into this problem and made big statements about the magnitude of the problem. This is from a statement paper, sort of a position paper by DeepMind. The lead author was Batalha. Many people participated in this study. That's what they say about combinatorial generalization, that it must be top priority for AI to achieve human-like abilities, and so on. So you can see that it's not just a minor problem, it's something that is really plaguing people trying to do more intelligent things with deep networks. And let me give you a concrete example of how we dealt with it, or where the standard systems in AI run into problem of combinatorial generalization. We saw this example before, in which we have a number of person-like images here with different properties. So we have different people and different properties. And the problem here for the network or the model is simply to get all the people out. There can be two, there can be more, but let's say two people. And so we know which person is in the image, and for each one of them, we want to know the properties, what hairstyle, what glasses, whether they have a mustache, what shirt they wear, and the properties that are allowed here in the model. Now, the way you test combinatorial generalization is the following. During training, we exclude certain pairs of person property. So for example, person 7, whoever that is, let's say this is the person that we call 7, and hairstyle number 3 are never shown together during the training. So you may see person 7 in many images, but not with hairstyle 3, and you saw hair 3 associated with different people, but not with person 7. So this pair is excluded, and here is another excluded pair of a person and glasses type. Is this clear? Because if not, let me know, jump in. And so this is a test of combinatorial generalization, because you want to know if the system trained on a variety of examples, when challenged with a particular combination that was not included in the training set, what happens. So the way we did it is comparing two models. One is our top-down, bottom-up, top-down model, in which you can give one task at a time. I want the glasses of a particular person, and then you cycle through the different people and properties. And in the other version, it's a standard neural network. I will not go into the details, but it's a very similar structure, but it does not get a task. There is no top-down instruction here. Instead, it has to output everything in parallel, the two persons and all the properties of each one of these person. And you compute the guided part, and you look at the standard neural network, what happens with the excluded person. So you can see that there are two things to compare here: our instructed model that has a task instruction and it's sequential, and the non-instructed and unguided model, which outputs simply go through the scene or the training in a single network and outputs everything in parallel. And the crucial test is what happens to when you test it finally after training, what happens with the excluded pairs. And let me show you this here. Maybe I'll jump immediately to the excluded pairs. We'll see the other in a minute. But this is the test of the excluded pair. The green bar is the performance of this instructed bottom-up, top-down model. And you can see that it does very well with the excluded pairs. And this low bar here, the blue, is the accuracy of the model, which is a standard bottom-up neural network trained for the task. You can see here what happens if you don't pay attention specifically to excluded pairs. You get that still this model is not as good as this one, but it's doing quite well. Here is another you can use, and it's not only us. People have done things like this in a variety of different domains. But here is another striking one. Here we saw a property before. Here is a particular relation, the relation of right-off. I can ask you in this image, what is to the right of the letter W? And if you look around, you will find that the answer is J. We trained in two networks, the instructed sequential one and the unguided parallel one, on this type of images, this array of letters, finding the right neighbor and the left neighbor of each one of the letters in this array. And again, if you go to the excluded pairs, and you exclude as before, so some neighboring pairs were excluded during training. You can see what happened when we test on the excluded pairs here. You can see that the bottom-up, top-down instructed model dealing with excluded pair is not different from the unexcluded pair. It's just complete generalization to new combinations. And these are the results that for the standard network that tries to get everything at once. I should note that when you look at the details, the parallel bottom-up is above chance. It's learning something. If it's trying to guess, it will not get to the results that we are getting. but it's really struggling. It's never getting the way, even with infinite training, that's basically with infinite, it's completely saturated here. It's not going above this about this level. And then something interesting here, I think, that's worth mentioning about attention and generalization. And what I mean is the following. In humans, seeing perception, it also evolves sequentially, as we've seen. It's guided by some attentional processes. And in human vision, the role ascribed to attention is usually to deal with capacity limitation. You can see here a quotation, sort of quote from the Encyclopedia of Neuroscience, and they have an entry where they define what is visual attention. And they say that visual attention is basically, it's a cognitive operation that is, its role is to deal with, efficiently deal with the capacity problem. We cannot do everything together. We have capacity limitation, and we have to decide what's relevant, filter out the irrelevant, and that's the role of, that's what visual attention does. And it certainly does it, but you can see here that there is another role for visual attention, I think, which I think, and here, Liad, you know better than I on attention, but I don't think that it has been discussed in the vision literature, that is a major role to play in combinatorial generalization. Because if you look, for example, at the example I've just shown you, if you ignore paying attention to the excluded pairs and to the problem of combinatorial generalization, the system working in parallel without any attention has no capacity limitation, there is no problem. It gets all 48 outputs in parallel. The accuracy is high, and at least for this task, it has no capacity limitation. So if you just think about capacity, there is no real role for attention in learning this task. But if you also pay attention to this, you see that even with capacity is not an issue, it's not limiting the performance of the system, you probe it with the need to do combinatorial generalization, and you see the failure. So I think here the task is learned well, but generalization is very limited. And I think this has implication, as I said, to human vision. It's interesting to explore further. I think that it looks like an important part of visual attention, and it's important for AI systems, because if you ignore the combinatorial generalization, and you will build systems that do everything without paying attention to this, they may fail the combinatorial generalization test or challenge. And when it comes to combinatorial systems, or to systems that deal with structured representations, as I think most cognitive processing deals with, you will run, this will basically limit your performance in such a way that it will not be it will not be of any real value. So I think that that's an interesting issue to take out from the combinatorial generalization study. So let me basically stop here. I'd like to mention, I will not go through the list of names, but these are people who participated in various parts of this, the results that I've shown today. There is a long and detailed description of all this work. There are a number, so far, just a small number of very partial papers, but there is a full description in a relatively recent archive paper that you can easily find, and those who are interested can look at the details. And let me end just with a graphical summary instead of giving you a list of points. We talked about structured complex scenes and then trying to understand them. I talked about doing this via a guided vision process rather than a bottom-up network, in which you have both the bottom-up and the ability to put goals and guidance explicitly into the system via the top-down network. that the structures are obtained from images using the combination of image and a goal via the automatic creation of a sequence of top-down instructions sort of injected into the guidance part in order to analyze the scene according to the goal the observer currently has in mind. And we also saw that once you have this particular structure that is guided by the top-down instruction, it turns out that it deals well and generalizes broadly to new combinations in a way that current models of the standard sort do not. So let me stop here, and within the short time still available, I'd be glad to take any comment or questions from the audience. So thank you for that.
Thank you very much, Shimon. And I want to ask everybody to, or whoever wants to unmute yourself and give Shimon a big applause. Thanks for a very exciting talk, emphasizing the giant gap that there still is between human and machine vision. And yeah, I mean, whoever wants to ask questions, as long as Shimon is here. Yeah, Jeremy.
So that's very interesting. The mechanism you've got sort of sounds like a serial self-terminating process of some variety. That leads to at least a couple of questions for me. One of them is there an explicit mechanism for keeping track of objects, items, people that you've rejected? And if so, how do you do that? And what happens if the target isn't present? Does this become serial exhaustive? And how do you know that you've exhausted the scene? Right.
So these are some relations to, I think, your own work, of course, on visual search and so on. So the and there are some similarities, and there is, well, you know, that there is some similarity in the structure of a serial process, and that can be exhaustive. So first of all, you keep track. As I said, you build incrementally a full representation of the scene analyzed so far, which I've not shown it, but you have the full positions and segmentation masks of everything you already identified and found. You know which class they are. You have the explicitly represented the relationships between pairs that you have. In a way that it's not just for termination, but after you, for example, you answer a question about this image, you can say, but is there anyone else holding a bag, for example? And it will be just a smooth continuation. You don't have to start from the beginning, analyze your image, but you have the partial interpretation with all the details, and you can go from there with reference to things we already extracted. With respect to exhaustion, yes, it will. If you ask, is there, for example, a boy with a particular clothing, for example, or something like this, then it will have to go, in this case, one by one through all the people in the image. By the way, it has the instruction next person, and it turns out that it learns it well. You don't have to say where, you don't have to distinguish it from objects. The instruction next person will give you the next person in the image, the one that is not marked yet in the segmentation maps that you already have, and eventually it will exhaust all the people in the on the scene. Now, I think that in most real scene interpretation, you terminate for other reasons. It's usually you do not, you do not have to search. You can do it. I'm just saying that typically you do not try to find the thing about find all the things, or to verify that something is not there. If you look for a boy doing something, you can look for the next boy, and if you no more boys in the image, then you terminate. So I don't think there is something very special about it, but yeah, this is what the system will have to go through in order to be sure that something it was looking for is not in the image.
My cat thinks you're brilliant, by the way.
The what, sorry?
My cat thinks that you are brilliant. He is currently walking around purring like a maniac. Here he is, purring like a maniac and butting up against your image on my screen.
Okay. Maybe interested in something in the screen. Yeah, right. Ellie, I see you there. Hi, Ellie.
I have a question.
Okay.
I have, good to see you. I have a minor question about.
Okay, so Misha, you after that. Okay, yeah, Ellie.
Problem.
Wasn't I called? Did I jump in?
Yeah, Ellie, go ahead.
Okay. The images that you showed were frequently small, and you even made a comment about this.
Which image, sorry?
The images size, the size of the images you showed was small, and you even made a comment about it. And at least in one, the one where girl facing girl, I thought that one of the girls that was not facing was actually facing in the opposite direction that your diagram showed. So I'm wondering why not show the images in the largest size you can to let the audience appreciate it, or the text. It's a minor thing.
So I apologize. It's just for the presentation, and you were.
Yeah, and the other thing that I noticed, and again is not really highly scientific, is that the scene in the lake with the grass that you created artificially struck me very much like the lake in Wellesley College where both your family and my family used to swim some 30, 40 years ago. So I was wondering if it's coincidental.
That's such an interesting comment.
Good to remember.
And I would say about the size and so on, of course, the thing for the system is we trained it, and it has its own capabilities. So sometimes for the system, sometimes can be only a few pixels and it still picks it up. There are some limitations for the system itself, but at least we trained the system in such a way that when the boys that we have or the bags that we have in the image are at such size and resolution that the system can deal with them. And in this sense, there is no big limitation, or we do not make any claims on the necessary size for the system or for humans to recognize something. In our case, it was not a limitation. In real cases, of course, it may be, and you may miss things because you do not have the sufficient resolution and size in the image, and so on. These are issues, but they go in a little bit more detail than what we can do now. It's now was really a thing that the more conceptual things of analyze how to deal with.
The problem is large enough that you can use small images, but.
Right, okay. Right, Misha.
Hi, Shimon. Well, I guess you mentioned it, but there are very interesting, I think, analogies with the language domain with what you're doing, right? And I think your top-down instructions to me sounds very much like questions and answering questions in the language domain, where you read a story and then you can answer questions. To me, it sounds very similar. But I was wondering if there is something like summarization or a gist extraction. Like, can you? Because when we look at the complex scene, we recognize without any instructions, like what's going on, right? And the rest are details. So is there any work on this kind of things?
Okay, there are many things here. Few sentences, but you raised many questions. I'm not going to answer all of them. I'll answer some of them, and we can take offline some of the rest. First of all, I'll start with the gist, because it's the last thing you mentioned. In fact, when we look at an image for a short time, we get only a part of it. As you saw, it really takes, even if you look at the Obama, if I showed you for 200 milliseconds, And object recognition, people is, talk about 100 milliseconds to recognize objects. If you saw the Obama picture for 200 milliseconds, you would probably not get the story of the image. So things takes time. Even the pouring girl, which is as simple as you saw to get to the bottle, was 500 milliseconds. It takes time to analyze scenes. It's interesting that we quickly get the important stuff. Otherwise, we'll be in trouble. But it does take time. But usually, we use this time very well, and within a relatively short time, we get to the point. And I think our system, to some degree, does it, but not always. The gist is something a bit different. And for example, what people mean about the gist of the scene, if you look at the crowded city streets that image, then the gist is to say that it's it's a traffic, and that's something that you do sort of independently, or people train networks and also to recognize the type of image. So not just recognize object, but to say it's a mountainous terrain, it's a busy street, it's a shopping mall, and things like that. This is treated more like sort of a class recognition. One of the things that you can do. So in addition to the recognition of individual object in the scene, you also get, as a part of things that you do early and quickly in the scene, is to get the gist of the image, which means, as I said, sort of the type of the overall scene that you get. And these people train models for it. It can be done pretty well. So in addition to what you have done, you can imagine that on this traffic scene, in addition to everything else, you will get sort of quite quickly during the scene analysis sort of the gist of it. And this, when you have no particular goal in mind, for example, it's something that can motivate you to ask some specific questions about the scene. And because these goals that I mentioned are typically generated internally in real life when you look at an unfolding event. You watch a movie, you are in a particular scene, and what you have in mind is, would the person now open the door of the cabinet or not? And you do have goals like this. Of course, when you just in an experiment, a slide is flashing on the screen, you have to start from scratch. But I think it's a very natural situation in which some type of a goal is generated internally. It doesn't have to be given to you from the outside as an explicit question, but it's sort of generated some structural question of some sort, and then you go ahead. I would just also, the last thing I will mention, that we have some version of applying the algorithm or starting the algorithm without having any goal. So it's empty, no goal. And then it's guided by some kind of built-in priorities. It's looking for people rather than before it looks for objects. It prefers to, if it finds interacting people, it spends more time exploring their properties than non-interacting people, and things like that we took from our psychophysical study. So you can start with some unguided, no-goal situation and sort of develop the goals as you go along based on some built-in priorities. That's the way we approach it at the moment.
Maybe I can just a brief follow-up, because for me the gist is mostly about action. So even like in the language domain, it's very clear, like who is doing what. Right. And so it's not just the type. You say, you can say it's a mountainous, but I wonder if people try to extract an action from the image, because that's, for me, if the image tells a story, the story is
absolutely right. So so you're right. I mean, your definition of gist is entirely legal, and that's what the scene is about. But when people talk about the gist of, that's basically sort of the it's not getting the action anyway. It's the term used for what you can quickly get about the global scene, and you get it very quickly, and that type of thing. There is a lot of psychophysical study about what you can and cannot get in sort of this kind of gist. But the gist you're talking about, the action, part of it, we are going in this direction. That we are looking for people rather than non-people. If a person is not interacting with anything, instead of spending time analyzing more, we go to the next person looking for interacting people. So what happens here, and I have even a slide for you, so we will not bother going into it, where I show the results of an analysis without a goal. And what happens is that you get initially the interacting people. Second priority is people who are not interacting people to people, but people who are interacting with object as opposed to just sending and not doing anything. And the lower priority is just person and then just object. So there is this kind in which you are not guaranteed to find the first thing you will find is the most interesting interacting people, but you will get to them relatively fast. That's what the system is geared up to do, to go for them as quickly as possible.
Okay, thanks.
Shimon,
Okay.
I'm not, you have any more
Oh,
time?
wow. Right, sorry, I'm over time. Yeah, I apologize, but I really have to move to.
Okay, so thanks again for joining
So,
us. It was
thanks.
a pleasure.
Bye, Jeremy.
Very
Thanks, everybody. And bye-bye. It's nice.
Bye. Thank you,
Nice
Shimon.
being-
Thank you, Shimon.
Bye. Thank you. Bye-bye.
Ciao.
Ciao.